Good morning, everyone. My name is Devjit Gopalpur. I work for the Platforms Networking Group at Google. We are working with ONF on the Stratum project. Brian's going to give you a short update on Stratum following this, right after. I'm just going to sort of set to give you sort of the set the stage, give you what the motivation is behind SDN and why SDN is important for Google, what are our current challenges, and why is the Next-Gen SDN important to us. So just to give you a little bit of history, so Google started out exploring the SDN paradigm more than 10 years ago. And the first sort of fully open flow-based SDN network that we deployed was called the B4. Many of you might be familiar with this already. It's the WAN network that connects our data centers together and carries all of the high capacity. It's the high capacity network that carries inter data center traffic, enables the reliable services such as things that you have come to be familiar with, such as Bigtable or Spanner and other Google services, and now for replicating state that related to Google Cloud, etc. So essentially, B4 was our first success story with SDN. And then we took this success and then applied it to our data center network, originally called Watchtower, and then transformed it, and which is called Jupyter now, which runs open flow based SDN throughout our global network in all our data centers. And it has worked tremendously well for us and has helped deploy solutions at velocity and helped us get the centralized control that we need to manage networks to differentiate between different applications, to give preferential bandwidth for, say, high capacity networks, et cetera. So essentially, this is running our data center workloads. So we took the paradigm of SDN again, and then enabled our peering network, which is called Espresso, to also be controlled by our SDN, centralized SDN controller. And today, pretty much all of our networks run SDN, and this is growing with increased need for capacity. So what is SDN paradigm at Google? So we run a set of applications in sort of, you can call it the central infrastructure or the local cloud. And this is the SDN controller, which is basically your rib, which is a flow programmer. And we want to control the network, which could be divided into separate domains, failure domains, connectivity domains, etc. Now, what are the challenges here? So today, it's a homogeneous network with almost a single type of silicon. Now, if we want to be able to innovate even faster, bring in devices from multiple vendors, and eventually come up, land up with this sort of a heterogeneous network, we have a problem with the interfaces. So all devices do not work with the same set of interfaces, and one interface doesn't work with all of the devices. So how do we solve this problem? So we are working in conjunction with ONF and some of the other industry partners to come with a set of interfaces. And over the last year and a half, have been working on standardizing these interfaces through the community called Stratum. And we'll talk about this in a bit in detail. So what does this give us? It helps us bring in new devices which have some unique capabilities that we want to exploit, and want to probably make one of our one part of our network sort of maybe low latency, or provide a special hashing capability for load balancing. So these are kind of examples of like why we want to bring in heterogeneous devices. And of course, the industry has also matured in terms of white box switches. So there are multiple vendors that can build the same set of switches. So we want to build a cooperative community that can build to a certain standard. So what is it that we are specifically looking for in this Next-Gen SDN? Basically, we want to be able to write a centralized control plane which is vendor neutral. What that means is we want to have a single network intent, have a descriptive language for describing a network role, and be able to compile it to different vendor devices. So with the advent of programmable hardware, this makes life a little bit easier. However, there is plenty of legacy or non-programmable devices out there that we still need to that are deployed that we still need to control. So we extend this interface and then push some of the hardware abstraction up the stack so that the control plane is now has more awareness of like the capabilities of the devices, and can more efficiently utilize resources and be able to come up with more innovative flows to program to different devices or to different parts of the network. And which basically gives us sort of a uniform interface to program the same set of flows to different devices. Another paradigm, another aspect of this is manageability and operability. So we are also proposing to use a uniform network model based on OpenConfig, which Brian is going to talk about shortly. So what this gives us is sort of a vendor agnostic view of the topology, and so operators can use a common set of tools to operate and manage all of the devices in the network. So this has helped us basically to roll out features at a much faster cadence, and to further utilize the advantages of a centralized control plane. So the software changes that we need to make either on the switching, on the data plane, or on the control plane are now more incremental, and we can focus our energies on optimizing the network to a finer level. And as I mentioned, this simplifies management and also to migrate some of our services. Brian.
Thanks, Devjit. So what this brings us to is a picture that is sort of what Timon was describing. So in this picture, we have an open source switch OS driving a NOS on white box switches, vendor-specific switches, and then we're communicating with a set of APIs to a disaggregated distributed control plane, which is going to be the focus of Thomas's talk. So if we break down the set of interfaces we're talking about more specifically, we start by defining our pipeline for our data plane using the P4 programming language. This is useful for both fixed function and programmable devices and serves as a contract for which the control plane can be written against. Then we use P4 runtime as an API for...
Hello? Oh, I think it's working now. Cool. So for those of you in the back, this picture is just the high-level Next-Gen SDN picture. We've got open source data plane on the bottom, a set of interfaces, and then a disaggregated control plane, which Thomas will be talking about in the next section. So the interfaces we're talking about is a P4 program for defining the pipeline. This serves as a contract between the data plane and control plane. We control the aspects of this pipeline, the flow table entries, the meters, counters, etc., using P4 runtime, an evolution of OpenFlow that's been a work from a broader set of vendors and service providers. For configuration and streaming telemetry, we have a set of OpenConfig models that have become broadly adopted by a large number of vendors, and we're using an evolution of netconf called GNMI. And then for operations, there's a set of microservices that have been defined in gRPC that enable us to do things like push new software, reboot the device, and do some amount of testing. So we pull all these interfaces together. The control plane will consume them, and then we have an open source implementation of all of them, and this is the Stratum project. So at a high level, Stratum is a modular agent that's broken up into a common area, which you can see in blue on the top. P4 runtime, GNMI, GNOI are gRPC services, and the gRPC server that implements those services is provided as part of the Stratum project. Then we have an interface that adapts these services to the vendor-specific pieces. On the left-hand side, in the green boxes, we currently have implementations using PI, which is program independent. It's for programmable hardware devices, and it enables us to map some of the configuration and flow programming constructs down to the switch SDK, for example, Barefoot's SDK. In the case of some of the fixed function ASICs like Tomahawk from Broadcom, we have a fixed pipeline mapping implementation that understands the definition of the P4 program and then provides mapping help from the P4 runtime calls down to the Broadcom SDK. On the right-hand side, we have an abstraction manager that helps us map the OpenConfig configuration models down to the platform APIs, the I2C bus, the /dev file system, etc. We leverage ONLP as a common set of abstractions on top of all the hardware platforms we currently support. And that enables us to take binaries and use them across different white boxes that are OCP or ONL compatible. We also have a chassis manager, which helps do things like the port mappings between the nodes or the ASICs and the front panel ports, as well as things like device initialization. So we can tell the story of Stratum's progress through a series of demos that we've done. The first demo, which isn't listed here, was actually done by Google at OCP last year. And they showed Stratum working on a white box switch, but it was still using a lot of Google's infrastructure. And what we've done over the past year or so is we've shown a series of demos on top of white box switches using the community code base and open source control plane. So the first demo we did was primarily a goal in feature parity with OpenFlow on programmable ASICs. So using P4 runtime, we replaced the OpenFlow driver and some OpenFlow devices, and we showed we could interoperate with ONOS and Trellis. This was demoed last fall at a number of venues around the world. This spring, our demos are focusing on how we can add OpenConfig's GNMI and GNOI to do common configuration and operations. And What this has enabled us to do is get device interface information as well as peripheral information from 3 different ODM white boxes using the same control plane driver. And then later this year, we're planning to show P4 runtime support on fixed function and programmable ASICs in a converged topology that kind of highlights the above. So flow programming parity, integration with ONOS and Trellis, as well as GNMI and GNOI support across a set of heterogeneous devices. So if you weren't at ONF Connect or some of the demos last year, we basically showed a 2-stage leaf-spine topology. This is very similar to some of the topologies you see in the access edge. And we used a combination of OpenFlow and Stratum-based devices. We had a P4 definition of our pipeline called fabric.p4, and we used the same set of applications, the Trellis applications, to control both of these types of devices in parallel. We also showed that with P4 and programmable devices, you can start to add value. We showed you could add INT, which basically enables you to carry data plane state throughout the packets and pull that off and parse it to get really fine-grained telemetry as to what's happening to your data plane packets. And we also showed VNF offloading, a way to take the data plane intensive pieces of VNFs and push them down to a programmable ASIC. This increases performance, reduces power, reduces latency and jitter, and overall this is going to give you better OpEx and better resource utilization. At ONS this year, what we're showing is a leaf-spine topology using Stratum devices, using P4 runtime, GNMI, and GNOI to program the devices and retrieve telemetry, statistics, and program interfaces. We're also showing some of the scalability numbers. So we're going to push 100,000 IPv4 routes and just show how this fabric can handle the load as well as some failure scenarios. For the demo, we're using white boxes from 3 different vendors, and they're all running ONL, and actually they're all running the same binaries. The only difference is the platform pieces. From a Milestones perspective, we kicked the community off last May. We had an initial seed contribution from Google, and then through last year, we got our first community switch up and running, and just recently, a month ago, we've exited the pioneer phase and started a new phase with 4 platforms and 1 software switch, where members of the community can start to preview the software and put it into some of the things that they're working on. The community's grown. We've added more than 50% of our total membership over the past year or so, and we're certainly welcoming. If you're an employee of one of these companies and want to start using Stratum, reach out to us, let us know. If your company's not on the list and you want to start using it, reach out to me or Timon, and we'd be happy to get you set up. So, thank you.
All right. Okay, so I'm not going to rewind, but basically I'm just going to continue here. Saying that we're taking this opportunity in the evolution, kind of a stable phase of the evolution of ONOS, to look ahead what's next. Especially with Stratum now becoming to prominence as a kind of a data plane portion of the next generation stack, we would like to make sure that the control plane is also adequately equipped. And so that's clearly, we're not abandoning the existing architecture of ONOS. That continues to evolve. We will be still cutting the regular cadence releases as we've been doing for the last 4 or 5 years now. That will continue, but in the meantime, on the side, we're going to be bootstrapping an effort which is going to construct next generation ONOS using some new methodologies and new tool sets. And so that's what I'll be talking about today. Some of the tenets, the core tenets, some principles that we would like to construct a new architecture on is to, first of all, center it on gRPC interfaces and standard Yang models and P4. Now, this is, of course, involves all of the interfaces that Brian already talked about, GNMI, GNOI, P4 runtime, as well as gRibbie, and, of course, the open config Yang model, and so forth. We also want to follow microservices principle. principles. So the platform itself will be far more modular in sort of deployability aspects. It'll also allow horizontal scaling of services and deployment of tenant-specific applications. Those are some of the limitations of today's ONOS or Open Daylight for that matter as well. Of course, we also want to rely on existing technologies that have emerged since then, so things like Kubernetes or Helm charts to be able to provide orchestration of the solutions. We want to reuse code as appropriate from the existing ONOS repertoire. So things like atomics or the user interface or other or protocol libraries may very well get reused. From the start, we want to focus on operational issues, things that will be required in production, as our experience showed us, things like live update, support for diagnostics, support for monitoring of the software itself, the whole FCAP suite, as well as various integrations with orchestrators such as ONAP. And of course, by following these principles, it will also allow us to use additional languages. We're no longer captive to Java. So most likely the next generation will be written primarily in Go, Python possibly, and Java also. Structurally, this looks very similar to what ONOS looks like today, with a couple of marked differences, in the sense that, yes, we will have topology subsystem, configuration subsystem, and control subsystems, but they will be separate, completely separate, apart from each other. We may still have protocol and libraries to adapt us to legacy devices, so we are by no means limited to work with only Stratum devices, but those, again, will be completely separate. And of course, the applications will operate in their own process space as well. So let me talk about a little bit some of these pieces. For the topology subsystem, we're currently exploring what models to use. One of the possible candidates is actually IETF model 8345, which was actually developed by our friends from Open Daylight and Cisco. Seems suitable. But that's just one of the options. Another option is we're exploring use of Google's unified network model. We've just started to initiate. We just initiated discussions with Google. The UNM was part of Jeff Mogul's presentation at Stanford last year, and he alluded to the fact they may be open to open sourcing it after some pruning. So we're just starting these discussions. Of course, fallback is always come up with custom gRPC APIs and to be able to stream topology information across the boundary. But most likely the middle option looks like something that we will be putting emphasis on right now. For the configuration subsystem, again, it will be designed as a separate entity, and its kind of primary objectives are to support multi-device configuration transactions, be able to apply configuration in an atomic manner across multiple devices. Also to be able to, even after the operation has been successfully, let's say, committed to the environment, we want to be able to support rollback, in a sense, roll back to the previous configuration. If something, for example, doesn't pan out, the validation missed something, and the configuration is not working, you need to be able to quickly roll back to a consistent state prior to this change. This is something we're going to be working on first, and the reason we want to be working on first, because this is something that lacks in today's SDN controllers. Again, ONOS or Open Daylight. The idea is to develop this and actually run it alongside of the existing ONOS 2.0 until the next generation stack is developed fully across the breadth of functionality. Southbound API for the subsystem will be GNMI and GNOI. Why? The primary reason here is that it will be able to sit right alongside, on top of Stratum without being able to have any intervening driver layers. Now, of course, if it sits on top of devices that today support, GNMI or that support the netconf or RESTconf or even SNMP, we can write an adaptive layer as drivers that will on top of it support GNMI, on the bottom of it support whatever protocol is required to talk to the device. On the northbound, it'll also support GNMI and GNOI in a sense that the protocol is the interface is very, very tight, very neat, and supports transmission of arbitrary models, and it supports transactionality, which is something that we would like to expose to the applications. Now, of course, the Yang models that we will be sending across southbound will be OpenConfig, and the Yang models that we'll be sending across northbound are yet to be determined. There will be OpenConfig, but then also some network-wide models as well. For Yang toolchain, we will be using ygot, again, part of the suite that is open source by Google. Has great support for translating Yang into protobufs as well as into various languages. You can either go directly to Go, or you can go to protobuf and then from protobuf to whatever 10 other languages that Google protobuf support. It's got an existing ecosystem. We don't need to reinvent the wheel here. The control subsystem, that'll probably come in actually last. And this is something where we're exploring use of new flow control abstractions. ONOS today provided kind of a flow objective as a pipeline agnostic abstraction for applications. While it definitely has its merits, it also has its downsides. And with the advent of P4 and P4 runtime, with the ability to actually prescribe what the pipeline looks like, or at least to be able to formally describe what the pipeline looks like, we can now expose the pipeline details directly to the applications. And this gives finer control and much tighter control without an intervening sort of abstraction or occluding layer that the applications can get over the control plane. So the idea is that we'll be protocol independent in terms of TCP and stuff like that. So we can actually free us from some of the header constraints, but it will be pipeline aware. And Carmelo can talk more about if you have any additional questions. The southbound API for this will be P4 runtime. Again, it's a well-defined, very low-profile interface, supports transactions, and allows direct use with Stratum compliant switches. And of course, adapters can be created for things like OpenFlow, dare I say legacy devices with OpenFlow. Northbound API is something still to be worked out. So this is kind of a summary of the picture with filling some of the information that we already know. GNMI on the south, GNOI and P4 runtime on the south. Northbound is yet to be determined for most of these subsystems. And so we're starting this effort. We started it formally earlier this year. Most likely this effort is going to continue the branding of ONOS. It's going to most likely be referred to something like micro ONOS, and eventually will become effectively ONOS 3.0. But it may take some time to develop because we're developing it with the, kind of with full participation of the community. ONF is not a team big enough to be able to do this ourselves. And so it may take some time to mature and take off the ground. But of course, in the meantime, ONOS 2.0 and its 1.0 long-term releases will continue to be made and deployed. And that's all I have. Thank you.